Mr. Sky Darmos. So let me take everybody out except for Sky. And Sky, welcome, sir.
An honor to be here. Yeah.
Oh, and you're over mute. Oh, wow, you're over mic'd.
Over mic'd? Why?
Yeah, which is good. Usually it's the other way around, but your mic is
Yeah,
way
I
too
bought it
high.
yesterday.
Can you turn the volume down a little bit?
Okay,
If it's,
over my
I think
on
that's
my
better.
computer. Is it
That's
better?
much better. Much better.
Okay.
Wonderful. Wonderful. So you have a presentation again, so let me read this here. It's composition dependent gravity and gravity control spacecraft. This is something that you sent me, and we've had kind of a back and forth about this. You've also been collaborating a little bit with David Chester on this. David,
Yeah, a lot.
yeah. So
A little bit. Okay. Yeah.
you're researching quantum gravity. You're going to describe a detailed analysis of Cavendish experimental results going back decades that support the idea that gravity is related to baryon number. And so this would mean that we can inflate the mass without increasing the number of particles to make a spacecraft or aircraft free fall more slowly. So it's a little bit of a different approach to it, but it's very, very interesting. And
Thank you.
again, you have put so much work into it. So you should be able to do the advance and the back and forth slide thing. I'm going to take myself out, and thank you once again, sir.
Yeah. Thank you very much for having me here. Okay. So this is SPD quantum gravity. SPD stands for space particle dualism. That's one very central concept. So space particle dualism theory started with an interpretation of quantum mechanics called the similar worlds interpretation. Now, this is quite different from the many worlds interpretation because the many worlds interpretation includes all worlds, even worlds where I'm not sitting here, I'm sitting somewhere else. But here we only have the indistinguishable worlds. And that means there's no measurement problem. As soon as I observe something, some worlds that used to be indistinguishable are not indistinguishable anymore, and that's how the measurement problem is solved. And also, there's no spooky action at a distance anymore because the spins are orthogonal on all the indistinguishable worlds, which are classical worlds. And so when I make a measurement, I find them to be orthogonal, and there's nothing strange about that anymore. So that problem is solved. And then we have also a means by which consciousness can influence the world, which you could argue is already part of the Copenhagen interpretation. It could or not. But here it's very clear that consciousness has an influence on the world. So that's very important because, as Penrose has argued and Lucas, Gödel's incompleteness theorem shows or proves that consciousness must be non-computational, and therefore the world cannot be only guided by physics. It must also give consciousness a chance to influence things. Then we have Wigner's dilemma, and that's kind of resolved by saying that all the observers are entangled. Let's get to the next slide here because we're in a bit of a hurry, I guess. It's a lot of slides. So Eugen Wigner initially supported the view that consciousness collapsed the wave function, but then he stepped away from that because he found it strange. He could not understand how you could do quantum mechanics in the space-time, because I observe you how you are in the past, and you observe me how I am in the past, and so then you're kind of led to solipsism. But when you realize that all the observers are entangled, then that resolves the problem, and you can have different people existing in the world, so there's no solipsism. But what you have is a cosmological solipsism, and I believe that's already part of the other interpretations. When you look at the many minds interpretation, or Max Planck's interpretation, where he says that you could commit quantum suicide and then you survive in your version of the world, but everyone else's version you have died. And so you see that already in other interpretations of quantum mechanics, or basically in all of them, we live in an island of entanglement, and so there's nothing outside of that island. And so yeah, so that would suggest that there's no other life beyond Earth. And one piece of data that supports that view very strongly is the CMB data, the CMB anomalies. We find that there are four major cold spots when you do spherical harmonics. You find that there can enter different numbers for n, and so the major cold spots, there are four of them, and they're in the direction of the north and south pole of Earth, and the direction of the north and south pole of the plane defined by the orbit of Earth around the sun. So the chance that this correlation is accidental is 1 in 3,500. If you if you just look at the chance for having such large cold and hot spots, that's 1 in 3,000 and 3,500. It is when you look at how well the cold spots align with the equinox and the ecliptic of Earth. And the numbers and formula I wrote here are about predicting the exact effect size. How big are the temperature differences? We know them to be 1/10,000th of a degree. And so by using the observer effect, so basically this would be a kind of a passive psychokinesis over millions of years. Like the dinosaurs basically already looked into the sky, and by observing the sky, they collapsed the wave function of the sky and the universe. And so the universe is created in a retrocausal fashion from the from the present to the past. So it's the present creating the past. Okay, so here we also see some non-Copernican structures. Now, before 2019-ish, before 2019, I attempted to explain these concentric ring patterns by saying that we dive into the spiral arms and then our view is obstructed and then less stuff is created. But that explanation doesn't quite add up, because the true distances, intergalactic distances that I found out in 2019, they show that the distance between the rings is much greater. It's not 2015 million light years, but 1 billion. So actually, the concentric ring patterns, one can explain them as baryonic acoustic oscillations, and that's how the mainstream does it, and that's how I'm doing it too, but using my theory and coming up with very precise figures for that. Next slide is so this is very central for the theory. So the first part was about explaining what a superposition is, what it means to be in many places at once. It's not the particles who are in many places at once. It's our consciousness, our collective consciousness, is located in all worlds that are temporarily indistinguishable to us. So that only would explain a probability distribution that is a mountain, not a wave. So we have to explain the waviness of the wave function. And we can do that by postulating that every particle carries its own quantum of space, which is an oscillating complex area 2 sphere. So the oscillation basically means that that it has a complex surface area, and the real part disappears as the surface area is described by a complex number z, and that goes around the origin of the complex plane, and thereby the real component of the surface shrinks down to 0, and then it emerges again. So every time that happens, the probability of detecting that particle on a particular pathway goes down to 0. So that's what makes the probability go up and down like a wave. And here around we see some formulas, like the radius of elementary spaces. The theory was born out of the. I was reading a book by Brian Greene. That was like back in 2005. It was talking about similarities between particles and black holes. It's a very popular idea. Was even mentioned in Big Bang Theory in the TV sitcom. Um, so, so the initial idea of space parallelism was that every particle was basically a black hole, but the surface, the event horizon, was viewed as a building block of space. But then in 2016, it turned out that if you use such small radiuses for your space quanta, then they cannot overlap to form a three-dimensional space. So basically, the elementary space had to be much larger, and actually they were scaled up in size exactly by the amount that that gravity is different from the electromagnetic force, and so you get very large elementary spaces, 10 to the power of so a resting electron, for example, would have a size of 10 to the power of minus 21 meters. And you can describe dimensionality, like you don't no longer say that dimensionality is 3, but you say it's 2.999999, and you have 35 nines here, and then you have a number, and so that explains why gravity is so weak. So gravity is explained by saying that there is a higher density of these elementary spaces here and a lower density here, and so particles are attracted to regions of space with a higher density of space quanta, and that's how you can explain gravity. And because there are already so many virtual particles, so most of space would be constituted of the elementary spaces of virtual particles. And so if you already have a huge sea of virtual particles, then adding a few an electron, the electron will emit virtual photons, and they will locally increase the density of space here. But it's a tiny increase because there are already so many virtual particles, and that's why gravity is so weak. Okay, so I won't explain all these equations here, but one can use this theory to explain the mass of the muon and the tauon. I was trying to do that since 2015, and I finally succeeded in doing that in 2023. And so basically, we view second and third generation particles as merged elementary spaces. It's a bit like black hole mergers. You merge together and you get something bigger. And to get the exact result, you must consider so many things. You need to consider how particles polarize the vacuum. There's naked mass, and then there's the observed mass, and all these kind of things have to be calculated. And you even need to include something that they call neutral particle flavor mixing. And actually, it happens with neutrinos, but I say it also happens with electrons. Basically, we just don't notice it because of some dynamics with the wavelength. So the accuracy is very high, 99.191% for the muon, 98.91 for the tauon. That was the first one, and then I got 100% for the tauon, which means agreement within margins of error. And the final version was 99.998% for the muon and 99.83 for the tauon. Okay, so so then we also have to introduce charge mass dualism. I won't talk about that long. I can just mention it briefly because it's not quite on topic. So basically, there's this electromagnetic mass theory that says that the mass of an electron comes from the energy that is stored in its force field, and I extend that to other particles, which to me is a very obvious idea, because when we look at the a neutrino, it's so tiny, and it's correlated to the it's associated with the weak force, and the weak force is so extremely weak. And I thought those two things must be connected. And at first, when you do the first calculation, they don't seem so connected. It seems off by a factor of 100. But when you account for all the running of coupling and everything, then it's very much correlated. And the mass prediction I have here is 99.84% accurate. So that's a pretty high, considering that pretty much nobody tries to even predict any particle masses. Then now this gravity theory, it in Einstein's theory, you have Einstein's field equation, and basically what Einstein did is he turned it upside down, and it's basically like a collapsing black hole. When you turn it upside down, it looks like expanding universe. And then people claim that that's how you could do cosmology, but I disagree. I think that Einstein's field equation are only made for one single object. You can't even calculate two objects together. You can't have an exact solution that includes two objects. So I do gravity differently, and I agree with Newton actually in this regard. And Newton was asked, if there's universal gravity, then why doesn't the universe collapse? And I agree with his answer. His answer was because the universe is infinite, and from every direction there's an infinite number of stars pulling, and so that's why nothing moves and it doesn't collapse. Now something is moving, it is expanding, and in my theory the reason for the expansion is entropy. So it's an entropic expansion, and that explains why it's accelerating. Now of course we know about the acceleration very indirectly from supernovae. They're too faint, and the accelerated expansion softens that problem, but it's still actually there. And only when you use my theory, it disappears completely. So it's very complicated in the mainstream to calculate distances using redshifts, because when you go above redshift 0.2, then you have to switch to another formula. The formula that applies in my theory, it applies for all the redshift regimes. So it looks a bit different from the mainstream. It doesn't have it has a 4 factor of 3 instead of 1. It has to do with how the universe expands differently. In the mainstream, it starts off very high, with a very high speed, which it must, because otherwise it would collapse back. And in my theory, it cannot collapse back. It doesn't have to fight gravity, and that's why it can start off very slowly. So you can have a universe that not doesn't start with a big bang, but great slowness, like a very slow. So it's the Hubble value. The evolution of the Hubble value is like a quadratic function, basically. And you can also so the small equation, the T0, that's actually enough to calculate it. The complicated one on top, on the left, that one is more precise, because it's looking at what the initial Hubble rate was and so on. Yeah, it's the results are basically the same almost. And so when you look at a black hole, the entropy in a black hole increases with the surface area. So it's proportional to the surface area, and since the surface area is something quadratic, that's why the expansion of the universe is also quadratic, the evolution of the Hubble value. This is the age of the universe. Here, 42 trillion years. Full age is even longer. And we can prove that. I can prove that with 8,846 supernovae. When you see SPD is the name of my theory, you see that the expectation line and the measured line is the same. And for GR, for general relativity, it's way off in everyone, except for those lower than 0.2, the redshift. And that proves that the distances must depend on a single formula, not on different formulae for different redshift regimes. So that's what this is proving. But also the average luminosity agrees with that I get agrees with theoretical predictions, while the general relativity one does not. Um, so we can use my theory to also calculate the exact weakness of gravity. We do that by calculating exactly how many connections there are from one elementary space to the next. And that's very complicated stuff. I'm not getting into that. It's too much to cover. So then there's this little idea of mine about faster than light travel. Since the time dilation is correlated to an increase in the density of space. So on Earth, you have both the background from the vacuum energy and you have the background from all the virtual gluons from Earth, and then gravity should be weaker, but it's not, because if you change a constant all over space, then it's basically becomes time dilation. And if you change one constant, you change all constants basically, and so it would also change the speed of light. So you could increase the speed of light by suppressing vacuum fluctuations, and you can do that with one can do that with a Casimir experiment, but that's very limited. It only suppresses some wavelengths. And maybe if one could use some macroscopic, create some macroscopic fractals, then that would suppress them a lot. But that's very speculative. I haven't actually written anything about that in my books, so I'm going over to the next slide. My theory also offers a method of testing wave function collapse. We can actually pin down when exactly the wave function collapses, which was not possible before. There was no such proposal before. We can do that by delaying the quantum eraser in the late quantum eraser experiment further and further to see until when we can still do the quantum erasure. And so when the wave function collapses, arguably you cannot delete the information anymore. And there's also a theory of consciousness, which explains qualia, saying that everything we experience there's a record of that. It's a bit like the Akashic records. And it explains remote viewing. It also explains qualia. So the redness of red would be correlated to all the experiences we had with this frequency. Okay, so back again to the time dilation. So speed-dependent time dilation can be explained by saying that because the size of space quanta is proportional to the energy, when a spaceship has higher and higher velocities, has more and more energy, and that's why basically all the space quanta are getting inflated, and if you change something fundamental like space quanta everywhere uniformly in a frame of reference, that's like changing one of the fundamental constants. And so it doesn't matter if you say you're changing g. Well, we'll later learn that there are different g's, but it doesn't matter if you change g or h or c. It all basically boils down to a Lorentz transformation. And so that's time dilation. And you have the same with gravity, but the reason for that is very different. The reason there is that the density of space increases inside a big gravitational field, like the gravitational field of Earth, and that weakens the gravity between two masses. But that is like a fundamental constant change, and that's why that translates into time dilation. And this meme here I created a year ago. It says that you can never reach the speed of light. You can get closer and closer to it, infinitely close. And the same applies to escape velocities of a collapsing object. It can never reach the speed of light, and so you can actually you cannot actually have a true black hole with an event horizon, because time slows down infinitely before that can happen. And my theory supports that view very strongly, because it says that we exist in all worlds that are indistinguishable to us temporarily, and that notion of temporality it means that there's an absolute frame of reference. So in which frame of reference is it simultaneous and temporarily? So so because no black hole can form from the view of an outside observer, so we say that it doesn't really form. It always remains a collapsing star frozen in time. And my theory also says that there's no Hawking radiation because, first of all, Hawking radiation, it violates a lot of conservation laws, baryon number conservation, lepton number conservation. You recall an evaporating black hole, it would basically turn into photons only and nothing else. So that's the only known way of destroying matter, basically, and it shouldn't be destroyable. And now that we know that the lepton number that now we know that electrons cannot decay and protons don't decay, so there's really no basis of violating these very fundamental principles. Also, the second law of thermodynamics is violated, but people argue that because the radiation goes into random direction, therefore entropy increases, but that's not a good argument, because when you have a sea of photons, you can measure each one of them, and then you know the entropy is very much reduced because you know the positions of things. So now let's get into the whole gravity business. So because in this theory, gravity is a side effect of the strong force, mainly the strong force, also electromagnetism, but mainly the strong force. So it basically a quark, it emits virtual gluons, and they increase the density of space. And so it only depends on the number of baryons, because it's only the number of hypercharges, basically. So you can calculate the G value of hydrogen by looking at the ratio between gravitational mass and inertial mass of iron. So basically you calculate out the binding energy in iron to arrive at the G value of hydrogen. So you divide the upper number 55.84 by the lower number 56.35, and you get the G value of hydrogen. And the basis of that is the G value of iron, which has been measured pretty well, I would say. I assume it to be 6.67428 for pure iron. The measured value is actually for stainless steel. The next slide. So here on the example of lead, here we do the opposite. We divide the gravitational mass by the inertial mass. So you can see here the different rows here are the different isotopes of lead, and the natural occurrences like 0.014 and so on. So the G value of lead is 6.6678. Okay, now molecules, they are pretty easy to calculate too. So hydrogen, so you have 2 hydrogen atoms, so there's a factor of 2, and then there's the inertial mass of oxygen in atomic units. So that's how you calculate this. 6.6618, pretty low value. So it's very good to do experiments with water. Okay, calculating the G values of mixed materials. Sorry for this big mess here. There are many different calculations here. So the only difference here is that we have to first calculate the atomic ratios. You cannot use mass ratios. So when you say 50% this material and 50% that material, that's not good enough. You have to actually know how many percent of this type of atom and how many percent of that type of atom. So you have to calculate that. So yeah, David Chester. No, it's hard to baryon lepton numbers aren't conserved. Thought that baryon lepton is conserved. Okay, good. Yeah, we can discuss that later. Well, it's only a minor point. It was about black holes. Let's focus on the gravity part. Thank you, David. So in practical situations, you always have, most of the times you have different materials for the source and the test mass. So the effective G value has to be the geometric mean of the two. So you see the square root there, the G value of the big mass, the attracting mass, and the G value of the small mass, the test mass. And you can see here that the correlation is very strong. The odds that this is a statistical fluke is 1 in 10 to the power of 69, extremely small. And a very new value is one from Wang in 2009. That's lead and SO2. Yeah, so on to the next slide. But this is very, very important evidence. It's basically the strongest evidence that I have. So here I did some own gravity experiments. So here I measured the gravitational constant of water. Back at the time, I didn't quite realize that test mass and source mass are equally important. I basically assumed that it's mainly the source mass that is important. But nevertheless, the difference is very small. These experiments are very difficult. And in a more advanced experiment, I would have to use a laser and the container would have to be transparent. The Cavendish experiment, you basically have two big masses and you have a beam with small masses, and the small masses are attracted and the beam is twisting, but the torque of the string, it pulls it back again, and so you get an oscillating motion. And so that oscillation period is 15 minutes and 50 seconds. And if Einstein was correct, it would be 15 minutes and 49 seconds. So if you try to do this kind of experiment, it's very challenging. And so 2 years later, I did the meta-analysis of all measurements of big G. So that was much easier, just relying on the experiments that are already out there. But this took me like a whole month to do this because I had not done the insulation right. So there was air coming in. And once I figured that out, it worked. and this was some other trials I did before, which were not classical Cavendish experiments. They were more like those type of Cavendish experiments you see on YouTube sometimes, where it actually touches the source masses. So here I was basically just looking at a chaotic system, like it was not isolated from air, looking at if it would turn faster for iron or for water. Like it would take 3 minutes to touch for water and 2 minutes to touch for iron. And I was doing that statistically, and look, it was like a race. And I did that 66 times or so, or even more. Yeah. So then we move over to free fall acceleration. And so basically in Newton's theory, what you have is for example, when you want to calculate escape velocity or free fall acceleration, I think that let's take the example of escape velocity. You have kinetic energy on the left side, and there's mass in it, and then you have gravitational potential energy, and there's also mass in it. And when you want to solve for the escape velocity, then the small m cancels out because it's both on the left and on the right side. But in my theory, there's no mass in the gravitational potential energy. It's instead you have a quark count, and that's this Y letter, blackboard bold Y letter, and the absolute value, it means the number of elements, how many charges are there, hypercharges. And so when you solve for that, then you basically end up with a stable ratio between the number of, it's still balanced with the mass is still there, but it's balanced by the number of particles. So you get a fixed ratio for different chemical compositions. And this connotation with blackboard Y is good for theory building, but it's not so practical because you cannot know how many. You cannot just put it on a scale that tells you how many particles there are. So it's more practical to use G values instead, use inertial masses together with G values. And so for the free fall acceleration, you can basically just use the ratio of big G's, because small g is different at different elevations and different gravities, but the ratio between the g values at one location of different elements, it will be equivalent to the big g values of those same materials. So there's this SAS drop tower experiment. It's not so significant, but it's quite interesting, quite impressive to watch. You see that iron, it falls at this faster rate than the aluminum capsule that was used in the experiment, and so it stays on the ground. And aluminum is the same material as the hull, and so it also stays on the ground. Lithium falls slower, and so it lifts up the ground, and also carbon, and also lead, and so they all lift up the ground. But the problem is beryllium and boron did not lift off the ground. It could be due to cohesion or something. Sass himself argued for that. So this experiment is not so significant in my own estimate. It's a 1 in 16 odds. Yeah. The neutrino free fall experiments are much more significant. When you look at them, we see here they I should actually use the cursor sometimes. We see that the values here, the theory and expectation. So we see that the free fall rate is lower in every single case. That's like crazy. Every single case, it's lower. That means, and if you do the analysis, you find that neutrinos fall 1% lower, and here the odds are 1 in 1024. It's not sigma 5, but it's one piece of evidence, and there are so many pieces of evidence. Next slide here. So I did my own experiments. Here I did some experiments with a release clamp and a receptor platform, and I found that the difference in the minimal free fall times is exactly as predicted. Yeah, so in this case it was 0.2 milliseconds from this particular height. And the reason why here we have to use minimal free fall times is because here it can only delay. It cannot fall faster. It can only delay. Then I did the same with release clamp and photogate. So here lead and steel, odds of 1 in 64, and the standard deviations were very high because the release clamp is very inaccurate. It's pretty messy. So I replaced that with a magnetic free fall mechanism, and here I got much smaller standard deviations and even non-overlapping standard deviations when increasing the height to 2.5 meters. Normally I was using like 2 meters. This was in one room. This was in Hong Kong. In another room, it was I got separated non-overlapping standard deviations in a second, third, fourth, fifth, seventh, and ninth trial. And here the combined odds are 1 in 524,000. Here in the next slide, we have a lead-filled sphere. Here I wrapped it up in paper because I had the theory that it shines through, the laser light could shine through. That didn't seem to be the case later on when I did some tests. So this is lead and this is zinc. And we see that zinc was falling faster 17 out of 19 times. And I would take care that the mass which supposed to fall faster was actually lighter so that nobody could blame the mass. So here the combined odds are 1 in 2 trillion. So the next one is wood zinc trials. Here the odds are 1 in 10 to the power of 20. So here I also got some amazing agreement in the time difference, 0.4 milliseconds as predicted. There's a slight difference here. 0.4 milliseconds difference is predicted for nutrient-rich wood, which has calcium, and 0.5 milliseconds if there's no calcium. And now we have the amazing experiments of Giorgio Toro. He did pendulum experiments, which were actually conducted in a vacuum, which is pretty impressive, and they're very careful experiments. And he sent me the results, and he conducted those experiments before even knowing about my theory, so they are not biased in any way. So, and the average agreement here is 99.97%. It's a 1 in 64 chance. And the next year, this year, he did more experiments, this time including plexiglass, which I recommended. Well, his value for plexiglass is not so good. It doesn't agree so well. But the agreement is now 99.95%, without plexiglass 99.96%, and the odds are the same. Although there's one more element here, or one more material. The hierarchy is not longer perfect. Before it was perfect, so the odds have not decreased further. But if you combine the odds, it's 1 in 4,000 something. Next slide. Now these are some balance scale experiments that I conducted at the beginning of this year. Let me quickly check the time. Okay, we have time. So here in the pictures you see I did experiments with gold, and actually here you can see a lot of elements. I have about 50-ish elements here. They are the size 1 cubic centimeter. And you can see here that I was using a balance, this one here, to measure the mass. And then I don't have a force sensor displaying Newton, so I had to use a regular scale, but with a lot of digits, a very precise scale. And I had to decalibrate them to have them show different values, and then track how the difference changes with the chemical composition. And that's what you see in these graphs here. Of course, in the future, I will do this with a very advanced device which displays Newton and will measure with a resolution of 4 micronewton, not micronewton. So here then I included more elements. I purchased more elements. Some of them are quite expensive. So I got this graph. Here I must say I did many measurements, and I chose the value that fits best, but the standard deviations you get there. And so these here, they were more randomized, like every measurement just taken once. And here I did many, and I basically so it's the best fit basically. And here but this here I measured only one time for each material. You see that the precision is not so high of these instruments, and that's why there are large standard deviations. So in the future I will get in maybe a month or so I will get a quite expensive device to measure very precisely the force, and here I expressed it in gram. I basically need 0.4 milligram precision, but not in gram, but in Newton. So that's 4 micronewton. So now to gravity manipulation. So as Tim Ventura, as Tim already explained, if you are able to increase the mass without increasing the number of particles, then basically this is your mass. It goes up, the number of particles stays here, so your number of particles per kilogram is going to be very low, and that's why you will have a very low G value. And you can do that by using fiber wires, but usually they are not hollow, but you can use hollow core fiber wires to accelerate particle using lasers. So it's like a wake field accelerator, but you have to use a very dense gas, possibly hexafluoride, hexafluoride, something like that. the densest gas or the second densest gas that exists, because some of them are toxic. This one is not. Um, then, but you cannot make a hoverboard, because with how if you go on top of it, it's supposed to be much bigger than yourself, because if you go on top of it, you're gonna drag push up the G value again, so that's not good. If you use this in orbit, in Earth orbit, then you can have artificial gravity, because basically the spaceship will fall slower than the people. The people will still fall at the normal rate. But if more and more people go into the spaceship, then the artificial gravity will start to wear off, or dissipate, as the orbits become more similar of the spaceship, and because the people, by standing on it, basically contribute to the total G value. Basically, they will be pushed to they will be in similar or natural orbits. So what you naturally have, if you have like only one or two people standing on it, basically you have different orbits for the people in the spaceship. The spaceship wants to go here, the people want to go there, but because they're in orbit together, they have the same speed, and so they're forced into the same orbit, and so they're pressing against each other. Okay, so now to some additional evidence about this chromogravity. You could call it chromogravity, also, or yeah, SPD chromogravity. So there's a mass gap between neutron stars and black holes, and it's very, very big. And basically, that's, according to my theory, that's because the masses that we have for neutron stars and black holes, they are wrong. They're calculated based on the gravity, and the gravity, I mean, it's wrong for Earth and all the other planets. The planets, the masses that we have are basically assuming that the planets are like iron spheres, because that's the G value that is used. So in fact, you need more mass to generate the kind of gravity that we observe Earth to have. So all the planets are actually a bit heavier, and the sun is 0.5% heavier. And but black holes are actually lighter, because there's this for atoms, you have this nuclear binding energy that reduces the mass, but doesn't reduce the number of particles, and that's why you have higher and higher G values when you go towards iron. So for black hole, that happens with the gravitational binding energy. Gravitational binding energy reduces mass, but it doesn't reduce the number of particles, and so then you have truly like amazingly high G values. For black holes, it's something like 9.8 or something, if I remember correctly. Actually, it's written here 9.44. Okay, cannot remember all of my numbers. For neutron stars, it's 8.017. So you have 15 to 20% nuclear gravitational binding energy for a neutron star, and you have 30% for black hole, and so that's a lot. And so black holes, in my theory, they are lighter to this amount, and neutron stars to this, and so there's a gap between them before, but as you translate to the SPD masses, the gap is closing in, so then you get a statistical gap that is natural. The next slide. So here I basically just calculate what I just talked about. Here we also have an agreement with the Tolman-Oppenheimer-Volkoff limit. I guess everybody knows Oppenheimer now, also because of that movie came out recently. So basically, the masses you see, they disagree quite extreme a lot with the Oppenheimer limit. But when you use my theory and the new Oppenheimer limit, based on that, then you have a very strong agreement. You have 2.08, and yeah, yeah, the values are very close. They're both about 2 sun masses. Okay, now we get over to some of my latest research. Composition dependent corrections to the perihelion precession of Mercury. So the Einstein's theory was agreeing very well with the perihelion precession until the year 2017, I would say. That's when Park, he calculated all the contributions to the perihelion precession, and when you do that, you risk getting too much perihelion precession, but you can't do anything about it because those planets all exist and they're all the comets and everything. So the only theory that could solve such a problem is SPD quantum gravity, because here you can actually reduce the perihelion precession, because if planets are really heavier than we think, then they're harder to move when subjected to the same gravity. So you get a little bit of less movement there. It's tiny differences, like 1 arc second in a century, but it's quite substantial. It's you get agreement, like when you take the data of Clemens, which is the standard. Actually, it's actually listed in Wikipedia as a standard, so to say, and you get disagreement for Einstein and agreement for SPD. So 99.79% agreement in value and disagreement in margins of error, and in my theory it's 99.98% and agrees. Perihelion precession of Saturn. Now it's tricky to talk about the perihelion precession of other planets because, admittedly, the perihelion precession of other planets are deduced from the perihelion precession. Like any deviations are treated as one factor, treating all planets equally, and so they're not looking at the deviation for individual planets. It's all like put in a big jar in a big melting pot. But there's some chance that the perihelion precession of Saturn that was reported, it was actually independent because it was based on some probe that was sent there. And here we have some excellent agreement, 99.9993% for SPD and 99.9990% for GR. And here both agree within margins of error. So here, quantum gravity corrections of gravitational wave induced orbit decay. So this is a bit complicated and tricky. Here I got like 3 pages in the slides, but to sum it up, basically both in the mainstream and in SPD quantum gravity, you would have to think that the Taylor pulsars, which are famous for confirming general relativity, that they must be white dwarf pulsars because their mass is way below the Chandrasekhar limit, and I mean with rotation you can have even heavier. You will have the Chandrasekhar limit is even a bit higher, so they are even more sure to be white dwarf pulsars. And in the recent last 20 years, we have heard more and more about white dwarf pulsars. It's not quite yet understood how they form exactly. It's easier to explain the high spin with neutron stars. So anyway, if we look at the gravitational binding energy and everything, according to my theory, they cannot be a neutron star pulsars. They must be white dwarf pulsars. And so here I calculated the G value of a white dwarf, or those white dwarfs, without accounting for the gravitational binding energy, and then accounting for it and everything. And then I get an agreement of 99.912% for my theory and 99.83% for general relativity. And there's no agreement within margins of error for general relativity since 2010. So things have become rough for general relativity recently, but nobody talks about it except of me. at least in those areas. But I think in most areas, nobody even talks about the problems with measuring big G and how that actually violates the equivalence principle. Okay, so this is the last slide. This is my most recent work. It took me 2 years of brainstorming to figure out why the composition dependence in the Edwards experiment, which is the standard reference for the equivalence principle, why it is so tiny actually that it was overlooked until Fischbach discovered it in the data. And so in this first picture, you see the method applied by Fischbach. I calculated this myself, but I was basically using his method here, but with my very precise G values and everything. But here we basically take the ad hoc modified adjusted values by Edwish. Basically, when he had a half full bucket of water, container with water, he would measure value and then double that because it was half full of water. And that's a crazy method to use. I mean, first of all, you cannot rely on mass ratios. You would have to rely on atomic ratios. But I mean, it was 1908, so it was atomic physics was not so very advanced by that time, like or barely existing. Yeah, he could not have known about binding energy, all these things, and so he didn't really have any expected values. He was just doing an experiment to try to prove what he already believed, namely the equivalence principle. So, but when we use more precise methods where we account for the composition of all the brass cylinders that were used to put various materials in, if crystal, copper, sulfate, and tallow, many different materials, so you will get a better agreement. But while here the odds are a bit lower, but the agreement overall is better when you look at it here. And we get excellent agreement here because here we actually calculate how weak the effect is, because here we have to calculate an effect and then divide by a factor of 100,000. Like, that's a crazy amount, and it's very ad hoc. Like, what would make this effect so much weaker? Like, what's the reason? And Fischbach simply thought, okay, it must be a fifth force, and that's where the popular term fifth force comes from. He proposed it, and he would have to use a coupling constant for that, and basically, instead of saying that gravity is the side effect of the other forces, he basically said the opposite. So here we also have to divide. Here we have to divide by a factor of 100 of 1 million. So, and here we have to do, we get actually too small effect and multiply by a factor of 100. So basically the adverse balance, it's basically looking at the gravity and the centrifugal force between two sides of a beam. And I mean, they're connected, they're one object. And that's why my expectation would be that you wouldn't get any composition dependence at all, but you still get some composition dependence because one side, the test mass on one side is hanging down and closer to Earth, closer to the source of gravity. That's why you get a tiny effect, and I calculate that tiny effect, which is at 10 to the power of -9 here. Yeah. So it's a very tiny effect, but the agreement is phenomenal, and actually all the elements agree here except for magnesium. But if you look at all the platinum pairs, you see that they their standard deviations are usually 2, and here it's 1. So basically, the accuracy of the magnesium measurement was overrated. So if you use the same standard deviation for all of the platinum pairs, then all of the elements agree. And here you have 4 different elements that don't agree. Okay, and this is my book. It has 760 pages. It's on Amazon. And it took me 10 years to write. I started in 2014 with just 50 pages, and now it's 760 pages. It's basically an endless story. All my research goes into that book, and you can. It's usually up to date. I update it every 3 months, so it gets bigger and bigger. So you get more and more for the same amount of money. Okay, that's all. Thank you for giving me the chance to speak here. It's a big honor because David Chester um, works for Tim, and yeah, I was eager to meet Tim, and yeah, thank you for letting me speak here.
Sorry about that. Okay. Sky, thank you. Thank you. David doesn't work for me. I just work with David. He's one of the usual suspects. That's what we'll call him. Let me bring everybody in, and I'm going to take the slide deck down. Everybody, please put your hands together and give Mr. Sky Darmos an enormous hand. Sky, it's obvious from your presentation that you have been working on that for many years, and it's absolutely tremendous. So thank you so much for presenting that. So I dropped a link into chat to the book on Amazon, but like people can always rewind the replay, right? This is live, so they can go back and pause it and look that way as well. So I definitely want them to check out your book on Amazon, and on the actual presentation page. We're trying to drop the presentations, and yours in PDF format is there, and it has the link in it. So
yeah, it's just a bit unfortunate that there was this glitch there with the PPT.
Oh no, don't worry at all about that. You know what? We have glitches all the time, but that's
I guess it happens to others too.
Yeah, it's part of the excitement, right? That's part of the excitement. So, yeah, thank you yet again, sir.
Thank you very much.
Okay, yeah, thank you yet again, sir.
Thank you very much.
Okay. Well, so I'm going to take everybody out except for Mr. Shiva Miyuchi. Yeah, thank you yet again, sir.
Thank you very much.
Okay. Well, so I'm going to take everybody out except for Mr. Shiva Miyuchi. And Shiva, welcome back, sir. So I have been begging for anybody who's watching, I've been begging Shiva to do more presentations